Welcome, everyone, and thank you for joining us today. My name is Paul Donahue. The topic for this morning's Tech Talk was determined based on input received at the recent IMS in Denver. This is a recording of TRM's CTO Shaun Moore's presentation on power combining considerations and trade-offs. We ask that you please mute your device during the session, and please submit any questions that you might have to me, Paul Donahue, via the chat feature, and we will respond promptly by email. Thank you.
My name is Shaun, I'm the CTO at TRM Microwave. I want to do a little housekeeping here before we start. TRM is giving away 2 Microsoft Surface Pros as part of this show here. So we're giving one away right now. It's over here. Just sent to my colleague over here. We'll be walking around. Just throw your business card in the box. Somebody here will win the Surface Pro by the time we're done. Moving on to what we want to talk about here is power combining. So power combining, and really, how do you choose the sort of power combining network that you want to have to be effective with what you're doing? So there's really 2 reasons why you want to have a power combiner. The first thing is you want to generate more power. You have an amplifier that generates so much power, you need more. So therefore, you put a bunch of them in parallel. That is one reason as to why you want to do this. The other reason is for non-coherent combining. Say you have multiple sources and you want to bring it onto a common line. Now, for the discussion we're looking at here, we're looking at really 2 devices that share a similar bandwidth, and therefore there's going to be a 3 dB worth of power loss for that sort of configuration. If you're going through and having something where you're 2 different frequency bands, then you can use a filtering sort of network, a diplexer, those sorts of things. That's really sort of a different application. I'm not going to speak about that today. We're really going to focus on the coherent combining situation. So really, what happens when you have a coherent combining situation is that you have 2 signals. There is an instantaneous summation of the vectors of those 2 signals coming in. So what happens is that as those 2 vectors add in phase with each other, those signals will sum. Anything that does not sum has to be delivered someplace else. Due to the law of conservation of energy, energy must be summed, it's got to go somewhere. So really, for an isolated combiner, it is combined, it goes into heat, and for a non-isolated combiner, it's reflected back to the source. A little bit of stuff here as far as how you actually quantify this sort of process here. In general, phase is your big thing you have to watch out for. Phase is really what drives the energy into the places where you don't want it to go. So, how do you estimate that? It is basically a half-angle sine squared function. You take the angle that you have, and you see the nomogram that I plotted on the left-hand side of the screen. So basically, you see you have a fairly flat line going up to about 20 degrees, and then she really takes off. The graph on the right-hand side shows exactly how that is set up, and with a variation of a little bit of amplitude variation, you see that really the amplitude doesn't do a thing until you get over 2 dB delta. They're almost overlaid up until you get to about a 2 dB delta. The black line on top shows the insertion loss due to phase imbalance. So really what happens here, and this is really why if you're talking about combining signals and you want to maintain signal integrity, why phase is also important. It's not just power loss. Take a look at the graphs there. We have the green line and the blue line. What they are those 2 signals that are separated by 20 degrees. The black line is a summation of power. There is a phase shift with the summation of power because of the way those 2 signals add. So there is an additional phase shift in addition to the efficiency rating of what you get. The red line is the power that is being thrown away. So with isolated combining, that power that is thrown away gets put into the isolation network. So there's usually some sort of a termination or an isolation resistor to absorb that. And really, especially if you start getting in combining networks where you have multiple units with more than 2, that phase imbalance can drive all the power into one isolation resistor. It does not necessarily divide equally. So that's something you got to be careful of. Moving over to the second half of what we're talking about here, which is called non-isolating combiners. These are things like radial combiners where that reflected energy does not go into into an isolation network. Where does that energy go? It gets reflected back to the source. The question I always get is really, where does that energy go, and how do I calculate how much energy is being reflected back to the source? If you think about the energy being reflected back to the source, it's really almost the exact same as high VSWR. It's really the same scenario. So how do you calculate that? You have the reflection coefficient that we have from VSWR. If you would just take that reflected energy and think about it as the reflection coefficient being added to the VSWR that you already have, that is the amount of energy that's coming back. So the example that I have on the screen here is if I have a power combiner that has a 1.21 VSWR, it has a reflection coefficient of 0.9. If I have a 20-degree phase error, or because it's a convenient number, that gives me a reflection coefficient of 2.6. Add those two together, you end up with an end resultant VSWR of a 1.7 to 1. So with no isolation network and 20 degrees with a phase error, you have an effective VSWR for your power amplifiers of a 1.7 to 1. Now, depending on if you have multiple amplifiers going in there, and TRM builds power amplifiers that have many inputs, that phase imbalance needs to be controlled very carefully. Otherwise, you can have a lot of power being reflected back to one amplifier because of the imbalance coming in through there. The chart there that's up there gives some examples as to how to relate the reflection coefficient back to the VSWR. I think that can actually be a very helpful sort of nomogram to help quantify exactly how much power is being reflected. So to start to sum up a little bit here, really, why are you combining? If you're trying to put multiple signals on a common path, and you're trying to have them in the same frequency space, these sorts of applications tend to run for parts, for example, that are on spacecraft where you have multiple local oscillators trying to get power onto a single line. In that sort of scenario, they share the same frequency space, and therefore there will be a 3 dB hit in insertion loss. A filtered version would not have that. But in that case, half that power needs to be dissipated in the isolation network. So in that case, if you're trying to do that, an isolated power combiner is definitely your best solution. And also, if you're trying to increase power, you could go either isolated or non-isolated, depending on how well your entire system is matched. It's not just the power combiner itself. Got to remember, the phase error that we're talking about here is related to both the power divider network, the amplifiers, and the combiner network. It's the net sum of all those phase errors that you have to look at, so we have to make sure we manage those going through. So for isolated combining, really the net type of networks that we use for that, traditionally, we like to use hybrids. And hybrids are really nice for several reasons. First, you have a 50 ohm termination to ground, which from a thermal management standpoint is very nice. It actually controls the heat that gets generated in a very effective manner. So we can use a 0180 hybrid or Magic T, and we terminate the delta port. All that differential energy goes to the delta port, the sum energy all goes through out the sum port. Another way to build that is to use ring hybrids, whether it's a rat race or a branch line or any of those sorts of hybrids. They work very effectively to do with that. Again, you have a 50 ohm termination ground. Another combination that TRM has been successful with is something called a Geisel configuration. It is actually a modification of the rat race hybrid where you can get multiple rings in there. You can have more than 2 outputs. We recently built one with 10 outputs as a high power combiner. It's a very nice configuration. There are 10 individual loads on there, and it balances the loads out. And it's, again, quite effective as an isolated combiner. The configuration a lot of people like to look at here actually is the Wilkinson divider. The Wilkinson divider is a beautiful device. It's got a lot of bandwidth. The downside of it is that actually the isolation resistors are in a balanced mode, which means that they're between 2 nodes and there's no path to ground. With a resistor in that configuration, in order for it to operate really optimally, you do not want a capacitive path to ground. It creates a parasitic that you really just don't want. So the result here is that you kind of get caught between a rock and a hard place. You have a circuit that you like, but you can't get the heat out of it because you don't have a good thermal path to ground. If you do put a good thermal path to ground, you typically end up with a lot of capacitance. So therefore, you'd be very careful if you want to use a Wilkinson-style power divider as a power combiner. Not that the resistors can't handle the power, but if you get a power with enough of a thermal path to handle the power, very often you end up with too much capacitance and it detunes the circuit. For non-isolated power combining, really what we look at here is things like radial combiners. That's tend to how these circuits tend to work. It's one of the most common ones, and they actually work out quite nicely. Now, from a product standpoint, you can see there, right in the middle, is a very large, that's a 64-way radial power combiner that we built. And as well as some of the other configurations for radial power combiners. Again, this is a very popular configuration. You can actually build this using airline, which means it makes them very low loss. Makes them very power efficient. You can run actually quite high power through these, and they will really, they do not get hot. As long as you manage your sources so that you keep your phase under control, this is a great solution. For isolated combiners, again, most standard sort of hybrids will operate. And again, we build these parts over multiple sorts of configurations. You see the big box built down at the bottom? That is a 10 kilowatt 4-way power combiner. These sorts of things can be built. You just have to manage the heat. And again, for smaller operations, for higher frequencies, we make those as well. So there's all kinds of operations that we do. What's important when you start talking about building power combiners is to go through and talk to some people like myself who make these things. We can discuss the trade-offs because there's a lot of trade-offs that can be made. And you have to understand the entire system with what you're trying to accomplish. And I think as long as we're careful with those sorts of things, we can be quite successful. I think that's, thank you very much. Any questions?
Once again, thank you for joining us today. We will be happy to answer any questions that you have submitted through email, which we will do promptly. You can also contact our free engineering hotline. The number is on your screen to discuss any additional questions you might have or to talk about your applications. Our next Tech Talk will be on Tuesday, August 23rd at 11 a.m. Eastern Time. Topic will be to be determined.